All right, let's get started here. We're going to cover in this lecture segment, I'm going to talk about forces. We're going to cover section 4.4, 4.5 of that chapter, and then we'll cover all of chapter 5. So, forces, what's a force? You can think an interaction between objects that I'll say when unbalanced, meaning only one force, or maybe multiple forces, but some sort of imbalance. When unbalanced, it causes acceleration. So that's the idea. And so just for a little review, I want to take a look at Newton's first law. There's 3 laws. If you know all of them, then you're going to know everything about motion because it all comes back to these, or a lot about motion. Newton's first law is also, well, actually, first it was found by Galileo, and that was called the law of inertia. An object in motion remains in motion. This is like with no forces, or maybe balanced forces. An object in motion remains in motion. Unless acted upon by external forces. Turns out internal forces between different parts of a single system, cannot accelerate the system. So it has to be acted on by outside forces. And so we can think about it like this. When F net equals 0, that's when there's the external forces. These are all this, when we talk about this net, those are external to our system. And the idea about this first law, it says, if the net force is 0, then acceleration is 0, and then the velocity is constant. Or not 0, velocity constant. It could be 0. 0 is one possibility of constant, but any other constant number, 1 meter a second, 1,000,000 meters per second, those are all also constant. So that's things tend to keep moving. And so I want to show you a little video here. And so here is a Muppet with some books on a chair. And we're in this little demo. I'm going to push this Muppet and illustrate the law of inertia. We get some motion and the slow motion. Look at what's happening there. Actually, I want to see it even again here. Okay, so let me take us back here. So what's going on here in terms of forces? We got some motion here. I have okay, so here they're moving, and before they hit the chair, they all have the same velocity. You got the velocity of the puppet, the velocity of the book, the velocity of the chair, moving at a constant speed, all of them moving together at a constant speed. Then, as we're going, we start approaching okay, so it's weird. This thing just doesn't tell me when I'm recording. Hopefully I'm recording. Yeah, I guess I am. It's really weird. It used to like have a nice thing where it showed you where it was recording. So what I want to say here is force creates acceleration. I want to get to the second law of motion. So here we come. As soon as that chair hits the other chair, you start having a force. So then there's this force. We can think there's the force of the one chair, the chair on the right, applying to the chair on the left. So if we can call this chair one and chair two, there's the force from chair one onto chair two. And this is, start talking about forces, this is how it's going to work. You're always going to have a force from chair, well, this is chair two on chair one. So chair two is applying a force to chair one. That is going to accelerate chair one. It's going to actually slow it down. And so chair one starts to accelerate, but the books and the puppet, they don't accelerate. They keep moving. So they're moving at a constant speed in a straight line. We associate them with the chair, but really they're moving on their own. And they only stop when there's a force applied to them by the wall and by that other chair. So you get only changes in velocity when there's a force. All right, so the idea here then is the velocity is constant when the net force is equal to zero. That's the first law. The second law, this is the one that we're really getting to here. The acceleration is going to be equal to the net force divided by the mass. And so you can see how the first law is kind of contained in the second law, because acceleration is the change of velocity. So when your velocity is constant, that must mean the acceleration is zero. And by the second law, the net force is zero. What is the net force? It's the sum of forces. And so we might write it like sum of forces. So you got to add up all the forces on the object acting on the object, and then divide that by the mass, and that will tell you the acceleration of the object. So getting to the third law, which we'll get to the applications in a little bit. But the third law has a nice rhyme that people have mostly heard. Every action has an equal and opposite reaction. And so that's one way to state it, although you want to be careful about what we're talking about here. Actually, there is no action and reaction. The whole reaction action is a little bit misleading. It makes it sound like there's a first thing and a second thing, action, reaction. Actually, these are two simultaneous things. You've got the force. That's what the action is, really. It's a force from one object to another. And then the reaction, we could think of force of A on B. One object applies an object to the other one. The reaction is the force of B on A. And that's really what Newton's third law is about. It says, basically, it's going to say forces always, and this is always, it's never, ever going to be not always. Forces always occur in pairs. Every single time, there's never just one force. There's always two. And they are simultaneous. And there really is no action or reaction. That's kind of in our mind's eye. They're simultaneous, they are equal. in magnitude and opposite in direction. That's the opposite part, is the direction. So let's say I have object A and I have object B. Maybe they're going to interact. They might interact by colliding with each other, or they might interact gravitationally. Maybe, let's say they're repelling each other. So then I'm going to have two forces. I'm going to have the force of B on A. Notice I put that on A. This is going to accelerate A because it's on A. Only forces on an object will accelerate that object. Then there's the equal and opposite. If A is being pushed to the left, B must then be pushed to the right because this is a third law pair, F of A on B. So notice you've got the two forces. One of them acts on one object, the other one acts on the other object. And so thinking about this, I'd like you to ponder this question for a second. Maybe pause the video and just to see if you can kind of figure it out. Looks like I cut it a little bit. In order to get an object moving, you must push harder on it than it pushes back on you. So take a look. What do you think about those? Is it true? Is it false? In order to get something moving, you have to push on it more than it can push on you. The answer here is going to be false. Why is that false? Well, you can't push harder. You must push harder. Equal and opposite. Think about that equal. It's impossible to push on something harder than it pushes on you, pushes back on you, because every action has an equal and opposite reaction. They must be the same. So people often get confused, like, how is it possible then to make something go anywhere if it's always going to push the same that you push? The answer to that is those forces act on different objects. They're not on the same object. So think about it like this. Let's say there's two objects, like we were talking about A and B. And let's say the mass of object A, 2 kilograms. Let's say the mass of object B is 5 kilograms. Now let's say they're repelling each other. So there's a force of B on A. That's a force on A. Let's say that's 5 newtons, right? So now object A is going to accelerate. It's like there's an acceleration of object A. It's the net force. There's only one force on A, FB on A, divided by the mass of A. And so that's going to be 5 newtons divided by 2 kilograms. And a newton per kilogram is meter per second squared. 5 over 2, 2.5 meters per second squared. That's how much object A is going to accelerate. But there's an equal and opposite. If B pushes on A has to push back on B. It's impossible not for it to do that. So A is going to push back on B. It's going to be also 5 newtons. It's going the opposite direction, but it's the same thing. So the idea is A is going to accelerate based on the forces acting on A, which there's only one. It's unbalanced. 5 newtons, you're going to accelerate. That's because there's no other forces on A. These two are sitting out in space. B applies a force to A. A is going to push back exactly the same as what B pushes on A, 5 newtons. B then will also accelerate. The acceleration of B is going to be its sum of forces. It just has one force, A on B, divided by the mass B. And so that's 5 newtons again. But now it's 5 kilograms. This is, 2.5 times bigger than object A. So it's a more massive object. It's going to accelerate less. 5 divided by 5 is just 1. the acceleration of B is equal to 1 meter per second squared. So there you can see you've got the same force, but yet they both accelerate because it's unbalanced. There's only one force on A, so it accelerates. There's only one force on B, so it accelerates. So going back to the question, there is a sort of intuitive thing here. You got to push harder on it than something, but it's not then it pushes back on you. What you could do is get rid of the second part of this. It's not how much it pushes back on you. It's you have to push harder on it than the other forces, other sort of balancing forces. And one of those would be like friction, for example. Let's say I want to move a box and I'm like, okay, I'm going to push on this box. I'm pushing as hard as I can. And well, let's say maybe I start pushing, 20 newtons and it's not moving. Say its acceleration is 0. It's not moving. So what does that mean? That means there's a friction. There's something else. It's not the equal and opposite. I mean, it is equal and opposite, but it's not a third law pair. These are, you can think about it like this. I've got the force of me on the box. That's one force. And the box actually is going to push back on me, but we'll leave that out for a second. That's the me on the box. And what's this, the friction? That's the force of friction on the box. Notice that's another object. So these are two different forces, both acting on the box. They happen to be equal and opposite because friction is sort of a balancing force. It's like the friction's only there because it wants that box to stay still. If I want to overcome that friction, I'm going to have to push harder and harder until I can overcome the maximum friction, and then it will start to accelerate. So you do have to push harder on it than some other forces acting on that object, but it's not how much it pushes back on you. It's always going to push back on you. If I push me on the box 20 newtons, then the box is going to push back on me. Box on me, that's going to be 20 newtons. And how is that balanced? If it's not balanced, if I was standing on ice, then I would probably slide backward. But what there's going to be another friction force, friction with me and the floor on me. And that's going to balance the box pushing on me. So there's all sorts of these different balancing forces here. All right, so let's take a look at a book sitting on a table. This looks like a boring situation, but there's a lot to think about because, well, one thing, gravity always acts. So you're going to have the weight of the book, call that the weight, W, mg. But what is the weight really? When we think about Newton's third law, there's something about Newton's third law. It always predicts every force has two objects. So you can always write a force having to do with those two objects. So let's think about what's the weight. What is the weight? It's the force of, gravity. We can talk about gravity on the book. But what is the object here? Usually we talk about one object and another object. What is the object that creates gravity? It's the earth. And so you can think of the weight as the force of the earth on the book. Those are the two objects, the earth acting on the book. But we can make an observation. What's our observation about the system? The acceleration is 0. This book is not going anywhere. It has no velocity. Its velocity is remaining 0. That means the sum of forces add to 0. There must be more than one force on this book. The gravity or the earth is pulling down, but yet the book is not moving. So there must be an opposite force, and that, of course, is due to the table. because usually forces need to be in contact. Gravity is one of the few things that there's no contact. And I actually should make that vector the same length. And so this is going to be we call this the normal force. And the normal force is essentially equal and opposite to the weight. So here's a weird little thing is you might think those are Newton's third law pair, because F net, the normal force, the sum of forces, what are all the forces acting on this? You have the normal force, that's pointing up, and so I'll call that positive. Then we'll subtract the weight, and then we get zero. And so the normal is equal and opposite of the weight. Normal equals minus the weight. That's by observation, because we're assuming there's only two forces. It's not accelerating, so they must be equal and opposite. So does that mean these are third law pairs? Is this the action and reaction? Is that what it is? Well, actually, no. It's not a third law pair, because a third law pair involves the indices, the force of Earth on the book. Okay, so what's the equal and opposite to the force of Earth on the book? What's the third law equal and opposite? What's the third law? You can think of it the third law partner, because there's always two. What's the third law partner? The way to do that is easy. You swap the order of the indices or the objects. F Earth on book, that's one force. That's the weight of the book. What's the other force? Here's a weird one, or surprising. Force of the book on the Earth. That's the third law pair. That's the third law partner of the weight. Basically, the Earth is pulling the book down. And so the equal and opposite is not the normal force of the table. That's a different object. But the opposite is the book is pulling the Earth up. And that's gravity. Gravity is symmetric like that. So if I have you got the book is there, the Earth is down here. There's your third law pair. You've got the force of the Earth on the book, and then you've got the force of the book on the Earth. Of course, we can't measure the force of the book on the Earth, because the Earth is so big, it doesn't accelerate very much. And so you can't measure it, but it's been measured in many other circumstances. So that's the idea here. So what about the normal force? That's here too. And so what's that normal force? And the way to do it is to always find out what are the two objects involved. The normal force as the force from the surface, surface of the table. So it's the force of the table on the book. So that's one force out of the pair. So if I want to get another force of the pair, it's going to be actually the book pushing down on the table. So the table is actually being pushed down by the book. And so there's the force of the book on the table. So that's the force on the table that will accelerate the table, except for the table sitting on the ground. And then the ground can also apply a force to push the table back up. So we've got all sorts of third law pairs here. We've got the normal force, which is the book, the table pushing on the book, and then the book pushes on the table. That creates one pair. And then our other pair has to do with the Earth pulling on the book and the book pulling on the Earth. So the way to do the third law is always just switch the indices. Force of table on book. The opposite, the reaction, if you will, would be the force of the book on the table. And the whole like action, reaction is that's made up. There is no action, there is no reaction. I mean, in engineering, they define it a little differently, but think about it like this. If there's a nail So you got a nail, and then you swing a hammer. The hammer comes down, hits the nail. We like to think, oh, the hammer's the action and the nail's the reaction, but they're simultaneous. So there's the force, you got the force of the hammer on the nail, and then the reaction you could call is the force of the nail on the hammer. But that's just because we're swinging the hammer. Like if let's say I were an ant or something. Let's say I'm an ant and I'm sitting on the hammer. What do I see? What do I see? I see that nail flying toward me, and then the nail rams me, and then I would say the nail was the action, and then the reaction was the hammer hitting the nail. So which one's the action? Which one's the reaction? There is no action or reaction. They're just a pair. It's a simultaneous pair. And so it's nice that it rhymes, but it's not really, they're simultaneous. So it's not like one happens and then the other one happens. All right. So I want to think about this for a moment. Why does the normal force occur? A normal force is any force from a surface that pushes up. So you got that book there. Why is there a normal force? Well, I mean, first you could think without the normal force, the book would accelerate down through the table. So the normal force is kind of like the table holding itself together. But one way the book describes it, and this is accurate, is like think about like a spring. Like if actually the table does sink down just a tiny, tiny bit. If you put the book like a micro amount, it sinks down. And so that compression, it's a kind of a potential spring energy between the molecules in the table produces that upward force. And so the third law can help us understand certain things. Like if I'm standing somewhere, let's say I'm just standing here, say my velocity is 0, then I need an external force to go somewhere, to go anywhere. I can't move unless I have an external force acting on me. So how do I get that external force? Think about standing on like ice, or like if you're floating in space, you can't go anywhere. If you're already moving, you'll just move at a constant speed. But if I'm standing on ice or something, you can't go anywhere. So how do you get, how do I get velocity? I need an external force. And so how do I do it? This is where friction comes in. And the third law, what are you going to do? What I'm going to do is think about when you're walking, you push backward. So you put one foot forward, and then what are you going to do? You're going to push backward on the ground. So the force of the person on the floor. I push backward on the floor, and then the third law accelerates me. Then the floor is going to push equal and opposite. This is a force of the floor on the person, and this is friction. It's a type of force it is. It's along the surface, and that's what accelerates me. So actually, without friction, we couldn't get anywhere. It'd be impossible to go anywhere because you need that friction. If this was a perfectly slippery floor, then my foot would just slide and I wouldn't go anywhere. But if you got some friction, then boom, you can accelerate. This is how cars, I think your book has some images like that, like this same kind of thing. Think about how the wheels turn on your car, the wheels are pushing to the left or behind the car, and then the ground pushes to the right on the car to accelerate. And there's a lot of rockets blasting off nowadays, putting all those satellites up there. If you got a rocket, what is the rocket doing? It's shooting out all that exhaust. That exhaust is actually, that's the thing that's pushing the rocket, because the rocket is pushing through some sort of fire or explosion. It's a force from the rocket on the exhaust particles. Those exhaust particles are being pushed downward. And so then the exhaust particles push upward on the rocket. So this is the force of the exhaust particles on the rocket. That's what makes the rocket go up. It's shooting stuff downward, and so that stuff pushes the rocket upward. We got millions of these kind of examples. Okay, let's try another little question here. A small car is pushing a larger truck that has a dead battery. The mass of the truck is larger than the mass of the car. Which of the following statements is true? So take a look here. Well, I won't wait forever. So you might want to pause this if you want to read them all. But the idea here is it's the third law. They have to be equal and opposite. So there's not too many tricks I can play on you about this third law. The third law is pretty straightforward. It always has to be the same. The car exerts the same amount of force on the truck as the truck exerts on the car. And then you may be asking yourself, how do you accelerate the car? Because there's friction. So let's say I got friction acting on the car. There's the friction from the road. You can think of that. That's the force of the road on the car. The other force on the car would be the truck. So it could be the force of the truck on the car. But those are the only two forces, sideways forces on the car. So if the friction force is bigger than the truck force, then the car can accelerate. And the truck will accelerate because it's getting a force from the car. So you've got the force from the car on the truck. Those are a third law pair, but one of those is on the truck and the other one's on the car. So the one on the car is going to try and accelerate the car to the left, but if the car has friction from the road, that arrow is smaller than the friction arrow. So you basically, if you want to do the net force on the car here, well, you've got two forces on the car. You've got the force of the road on the car, call that friction. And then I'm going to add here, even though it's actually subtraction, I mean, it's adding two opposite vectors. So the force of the truck on the car. So think about it like adding tip to tail vectors. I've got the friction going one way, and the truck is subtracting some of that force of the truck on the car. And so your net force is to the right there. So even though the truck pushes on the car equal to what the car pushes on the truck, the net on the car, I'm analyzing just the car here. The truck would be analyzed separately, but this is just the car. If you want to think about what's the car going to do, it's got the force from friction pushing to the right. It's got the force from the truck pushing to the left. And if the friction is bigger than the truck force, then it's going to net accelerate to the right. All right, so let's get on to the next section, which is applications, 4.5 applications. And to keep it short, I'm just going to do the examples here because I think they really, that's kind of the point of this section here. So let's take a look. All right, this is a good one to go over. example 3, air resistance. And as an 8-kilogram rock is falling from a high cliff, it experiences air resistance, which increases as the velocity of the rock increases. At a particular instant in time, the rock experiences an upward force due to air resistance of 30 newtons. What is the gravitational force on the rock? What is the direction of this force? And that's A. B, what is the net force on the rock? What is the direction of this force? C, what are the magnitude and direction of the acceleration of the rock at this instant of time? Well, let's just think about the rock as it falls here. So let's say t equals 0. You're going to drop the rock. Someone is here, and they let go of the rock, and there it is. So starting out, velocity equal to 0. What's happening though? It's got force on it. You've got the weight, the force of gravity. You call it the W, or you can call it Fg. What we told you is it's the mass times the acceleration of gravity. So this is going to answer question A. Actually, this force is always the same on the rock. It doesn't matter when. So let's give it a shot here. It's 8 kilograms. And let's use the approximation 10 meters a second squared for gravity. That gives us 10 times 8 is 80. And then the kilograms times meters per second squared, that is a Newton. So we've got 80 newtons is our force. And that's the answer to A. It doesn't matter. And it's down. If you want to make these vectors, I'm going to call it down. All right, there it is. And so then the rock starts to accelerate and have some velocity downward. And so there you got the rock, and then it's going to fall again. It's going to keep falling. And what's going to happen here is the weight is always going to stay the same. It doesn't change. But you start getting friction, air resistance. I could call it air friction. It's a little bit different than friction on a surface, but it's a force that slows it down, right? And opposes the general motion. So that force, as it picks up velocity, the velocity is 0, but as it goes down, it's going to go faster and faster. And the faster you're going, the more air resistance you're getting. And so this is going to subtract from the total. You could think your F net is the weight plus the air friction, force of air drag. And why do I say plus? Because it's adding vectors is the only thing there is. There is no such thing as subtracting. If they're subtracting, then they have opposite directions. And we see they have opposite directions. So it's like you got one vector coming down, the weight, and then tip to tail, we're adding the air drag going back. And then the net force is what's left over. And so we're adding them together. You're going one, it's like imagine I walk down and then I walk back up. And the difference from where I started to where I finished, that's the net. I started up at the top, I came down, I came back up. So now I've gone a smaller distance, effectively subtraction. So you can think of it like this, as like 80 newtons down. Then you could say plus 30 newtons for the air drag, but that's up. And so if I want to switch it to down, it'd be like 80 newtons minus 30. Because when I switch that up to down, I get a minus sign. And so it's effectively subtraction. And so we end up with 50 newtons down. That's the net force. And right, so that's B. And then C, let's try C here. What are the magnitude and direction of the acceleration on the rock at this instant of time? We know its net force is 50. And so acceleration, F net divided by mass. And so we've got 50 newtons divided by 8 kilograms. And that sounds like 48 is 8 times 6. So it'd be like 6.25 meters per second squared down. So at this point, it's still increasing its speed. It's going to, as long as the weight is bigger than the air friction, it's going to, that velocity vector, which is the green vector I was trying to say, you got the velocity, it's going to keep growing. And so this friction is going to keep getting bigger until it equals the weight. And then we call that terminal speed when it reaches the speed where it's basically, it's in equilibrium. But this problem doesn't go that far. I have no concept why they didn't take it that far. All right, so let's try another application. This was example 3, and let's go to example 4. Connected objects. This is a great one for the third law. So here's the connected objects they're talking about. So let's take a look here. 2 connected carts are pulled across the floor under the influence of a 36 Newton force applied by a string. All right. The forward cart and its contents have a mass of 10 kilograms, and the second cart has a contents of mass 8 kilograms. Assuming that frictional forces are negligible, what is the acceleration of the 2 carts? And what is the net force acting on each cart? So here we're going to like draw a circle around the system and say, this is our system. It's accelerating together. Like it's not this little hook, you know, the relative locations of M1 and M2 are set. And so they're moving together. This is an external force. It's acting specifically on M1, but since M1 is connected to M2, we could consider it acting on the whole system. So A is pretty straightforward. Acceleration, net force, external, and there is gravity and there's normal force, but those are up and down forces. I don't care about up and down. We know they balance. We're just, this horizontal force needs to be balanced by other horizontal forces, but they tell us friction forces are negligible. So this is the only external force. And so we're going to divide that by the total mass. And so we've got 36 newtons. We divide by the total mass, 10 kilograms plus 8 kilograms. Add them up, 18 kilograms. And then what's the 36 divided by 18? Sounds like 2 meters per second squared. That's the acceleration of the system. The next question, this is the interesting one. What is the net force acting on each cart? Interesting. So now we're going to divide this up. We're not going to consider one system, but think about it like 2 systems. Let's think about M2. This is more of a simpler one because what's the force on M2? The only force on M2 is that hook pulling it. So this would be the force from 1 on 2. That's the only force applying on M2. So we know the M2 is going to obey Newton's third law by itself. So the net force on M2 is going to equal the acceleration of M2 times the mass of M2. And this will tell me that force 1 on 2. That's the force accelerating M2. And the thing is, we already know its acceleration is 2 meters per second squared. They both have that acceleration. So I'm going to plug that in, 2, and then I'm going to multiply by the mass of M2, 8 kilograms. 2 times 8 is 16. That's 16 newtons. That's what is actually pulling on M2. So let's continue and now analyze M1. So let's try M1. And this one has 2 forces acting on it, because we've got here one force pulling it one way and another force pulling it the opposite way. This is the force of 2 on 1. Notice we have a third law pair here. Force of 1 on 2, force of 2 on 1. They are equal and opposite. So here, the F net on M1, well, we've got 36 newtons pulling one way, and I'm going to subtract off F2 on 1. That's a force dragging M1 back. Of course, you can imagine if M2 wasn't there, M1 would accelerate more because all 36 newtons would act on it, but it has to share some of them with the other cart. So they're going to subtract. So what is that F2 on 1? That's actually, we already found that out. It's 16 newtons. We found that from M2. So minus 16 newtons, 36 minus 16 is 20 newtons. That's one way to find it. We could use the same method we did for M2, though. I can say F net on M1. Well, it's this. What I did here is the sum of forces. I knew one force was 36, and I knew the other force was 16. But the other way to do it is to use the MA. Oops. So here I can say it's the acceleration of 1 times the mass of 1. So what's the acceleration? Well, that was from part A, 2 meters per second squared. And then I'm going to multiply by the mass of 1, 10 kilograms. 2 times 10 is 20. 20 newtons again. So that's generally how you like to do physics. You can try and get the same answer for 2 different ways. Then that helps you, helps say that it's consistent. Maybe it's right. So that's B. All right, so let's get on to chapter 5 here. And it's a circular motion chapter. And it's called circular motion. But it also includes planets and gravity. The planets move in approximate circles, so they actually is a nice place to take it all together. So centripetal acceleration. This is centripetal means like center seeking. How can we describe the acceleration involved in changing the direction of an object's velocity? Centripetal forces, centripetal center seeking. So center seeking forces. It's weird, this outline. They're not talking about circular motion. That's really what they should start with. What types of forces are involved in producing centripetal acceleration? These are things that have to do with what's called uniform circular motion. That should probably be the first section of this chapter. But I guess they're trying to make space for the planetary stuff. So let's get into the basic idea of uniform circular motion. Start off with that. And the uniform part, what does that mean? That means the speed is constant. And so let's think about something moving in a circle. You could have many different things. For example, let's say here, the moon going around the earth is approximately circular, or maybe if you're swinging a ball on a string, something like that could be circular. Let's imagine we're going in a circle. So say we've got like this pathway here. There's our path. And let's say I have a ball going on this path. So we've got some sort of ball, like maybe it's right here. And let's say it's zooming around, going around in the path. The idea here, first idea, is that the velocity is parallel, or actually there's a word here I'm going to use, tangent to the path. And unfortunately, these basic concepts we need to, the word tangent needs to be described. So what does that mean? Tangent means like single touch. And so if you think about, I've got a curve here. Look at this curve. Single touch, and actually by what? By a line. By a line. So imagine a line that kind of comes through and only intersects this circle at one single point. It's kind of a weird thing because imagine I'm coming in with a line like this. This line, notice, intersects at 2 points. 1, 2. That's not the line we're talking about. We're talking about single touch. Tangent is single touch. So it can't intersect at 2 points. That one's not going to work. So I'm going to X that out. Oops. That's not tangent. Where's the tangent? The tangent is a line that only intersects at 1 point. And so if you think about where that ball is, the tangent line is some line that comes in and just barely touches the circle. That's the tangent line. So here we get tangent line just barely touches the circle. And that produces the direction of the velocity. The velocity is tangent to the path. So when the ball is right there, that velocity is going to be straight up. And let's imagine this ball is sort of going around the circle. When the ball gets up to the top there, what is the direction of the velocity? Velocity's over to the left. That would be the V at the top. And so on. It's gonna keep going. And I gotta get rid of some of my other stuff there. Let's say that ball is coming around, and I might ask this, or you could get it on your homework, like, what's the direction of the ball when it gets to that point on the left? Well, it's tangent to the path, so it's exactly straight down. That would be when it's the velocity when it's on the left side. And maybe the ball, we could talk about an intermediate, like sort of like right there, sort of halfway between the left side and the bottom side. Now the velocity's at some angle, like that. So the velocity is, it's always going around. It's like following the path. But at any one instant, the velocity itself is in a single direction. I made this curvy arrow, but at any point, the velocity is not a curve. The velocity is a straight direction. But let's think about two different points. Like, for example, we have, it's called V1. Got V1 right there. And then here's going to be V2, like this. Now the length, which is the speed, is staying the same. I got V1 and V2. I want to know their difference. So let's draw them with their tails together. I have V1 here. V2 is the same direction, or I'm sorry, the same length, but a different direction. And now we're going to figure out what do we need to add to V1 to get V2. Imagine I'm like walking. I want to end up over here at the tip of V2. So I'm going to walk up, then I'm going to walk over like that. That's my delta V. That's what the acceleration is doing, delta V. So imagine these 2 points are like related to the center of the circle here. You got these radial lines. And so you have one velocity. There's some sort of force. Notice there's a force. Even if you're going at a constant speed in a circle, if you're turning, there is a force on you. And we see the direction of the force because V1 plus delta V is V2. So that delta V, that's the direction of the force. And look at what direction it points. That's your acceleration. That points toward the center. And that's what the first topic is. Centripetal acceleration, center-seeking acceleration. Well, we found out, and I put this in the middle because it's sort of an average of the first point and the final point. The average acceleration points there. But if you were to do instantaneous, what you'd find is at every single point, the acceleration is going to point straight toward the center. And that's a property of uniform circular motion, is that you get a centripetal or center-seeking acceleration. And of course, that acceleration is due to forces, centripetal or center-seeking forces. So we can now imagine that, like, I got this ball, we're swinging it on a string here. It's going in some sort of a circular path, and it's got to have that centripetal force. And it's, in this case, in the case of a string on a ball, it's the tension that's going to create the centripetal force. The tension is the centripetal force. In the case of the Earth and the moon is actually going to do a circle around the Earth. And so gravity, this same thing that pulls us down towards the Earth, that's the centripetal force here for the moon Earth system. The gravity's pulling in, and the moon, if the moon weren't moving, if the moon were just sitting there, then the moon would accelerate toward us and it would ram the Earth. But the thing is, the moon is moving. So even though it's being pulled toward the Earth, basically it's kind of like falling towards the Earth, but it's also moving sideways around the Earth. So it never actually hits the Earth. All right, let's try an example question here. And here we go. Sample exercise. And I think there's a formula which it take a long time to derive the formula, or not that long, but long enough that I'm not going to subject you guys to it. But the centripetal acceleration, and probably not the most useful thing to, it's really just a plug into a formula. So I really don't know why I have you guys doing this. It's not too insightful, but they tell you it's something to calculate. The centripetal acceleration, this is not obvious, but it's kind of a cool little formula where the acceleration is the square of the velocity divided by the radius. So anytime you're going in a circle at a constant speed, that's your centripetal acceleration. And then there's of course, a centripetal force, which is, it's not necessarily even one force. It might be multiple forces, but it's basically it's the sum of forces. The sum of forces produces a center seeking net force. So when you think about a centripetal force, it's really the net force. It's like, I got this ball here. This ball has the weight acting on it. It's also got tension acting on it. Those two together produce a center seeking force. And so your centripetal force is just m times the centripetal acceleration. And so that's m times v squared over r. And I write the equal sign again. One time someone asked me, why isn't there anything there? It's the centripetal force. Sometimes you don't want to write the left side of the equation every single time. You write it once, and then you can change the other side of the equation. So let's take a look. A ball has a mass of 50 grams, otherwise known as 0.050 kilograms, and is revolving at the end of a string in a circle with a radius 40 centimeters. The ball moves at the speed of 2.5 meters per second, or 1 revolution per second. I don't know why they have it like that. What is the centripetal acceleration? What is the horizontal component of the tension needed to produce this acceleration? Right. So it's plugging into the formula. So A is just v squared over r. So we're just plugging in the numbers they gave us. 2.5 meters per second squared divided by the radius of 0.4 meters. So we can take a look at this in little pieces. Of course, you can try and figure out how to plug into your calculator. But first, I want to look at the units. Well, I'm going to have 2.5 squared divided by 0.4. And then my units, that square has to act on everything in the parentheses, including the units. I got to square the meters. I got to square the seconds. And then in the denominator, I have another meter. And so I'm going to get some canceling of the meter on the bottom and one of the meters on the top. And then I'm going to get meters per second squared. So it's an acceleration. Velocity squared. So velocity squared divided by distance is going to give you the units of acceleration. And then we do a 2.5 squared divided by 0.4 is 15.65. So you get an acceleration here. 15.65 meters per second squared. But notice they're only giving me two significant figures, 2.550. So I only have two significant figures. I need to round this to two significant figures. So that's going to be 16. I don't really, this 0.65, that's a little sketchy because that would assume I knew more digits here than they gave us. All right. All right. So what is the horizontal component of the tension needed to produce this acceleration? Well, that horizontal component, that's the centripetal force. You've got a vertical component of the tension, which is canceled by the weight. So you could think about it like this. Your net force, which is the centripetal force, is like it's the tension plus the weight. And so the tension is like going up like that. And then I'm going to add the weight to it coming down. And then that's your net force is like the sum. The net force is going horizontally. The other way to think about it is the vertical component of the tension cancels the weight, leaving you with only the horizontal component of the tension. So that's what we're trying to find. And it's just the tension horizontal is the centripetal force. And so it's MA. MA is the net force, or is the sum of forces. We know the M is 0.05 kilograms. Then we'll multiply by, actually your book keeps 3 significant figures in this example. So they call it 15. Actually they call it 15.6. But there's a 5 there. I would round that almost to 15.7. So I'm a little bit not agreeing with the book's answer. But it's either 15.6 or 15.7. I think the thing is, if you tend to round before your final answer, you can get errors that will add up. And so here we're going to multiply by 15 actually, I'm going to keep an unrounded value. I'm going to use the unrounded value just because that's generally what I do, so it's consistent. And then, oh, you know what? Now I understand. I miswrote it. It's 15.625. So that does round to 15.6. So I had it wrong. The book had it right. 15.625. Then multiply by the mass, 0.05. And we get a smaller force, well, less than a Newton, 0.781 newtons. All right. So the basic idea here is any circle, whether it's a car, doing donuts on a parking lot, or a Earth orbiting the sun, that's an ellipse we'll get into, but it's basically a circle. The basic idea is there's got to be an inward force or multiple forces that add up to create an inwards force. In the case of the car, it's friction. Friction is the centripetal force, you could say, that pushes the car inward. So that's why if you go too fast, you're going to skid out. But until you overwhelm friction, that friction is going to point toward the center of the circle. If I'm the Earth going around the sun, then there's got to be some sort of centripetal force. In that case, here it's gravity. It's the force of gravity. You could call that the force of the sun on the Earth. The sun is pulling the Earth inward. If the Earth were not moving, let's say we had no velocity, if we were just sitting there, we wouldn't last very long because we would accelerate toward the sun. Well, we're already accelerating toward the sun, but we'd start moving directly toward the sun. We'd go right into the sun, and then we'd be done. But luckily, we've got some velocity to the side. So it's like we're being pulled. And so we start developing that velocity. You're starting to develop a leftward velocity. But by the time we've got that leftward velocity, we've moved out of the way. So that's the general idea. All circles work like that. Uniform circular motion. All right. All right, so now let's get on to the next section here, planetary motion. And here it's a little bit of history the book gives us. We want to consider first, how do the planets move around the sun? That one we can kind of already answer. The idea is the sun pulls inward via gravity, and the planets, they got original speed. So they had some initial velocity from a long time ago when the solar system formed. And that's why they're still here. So the planets move in roughly, not roughly is the emphasized word here, roughly circular motion. So the inward pull of the sun, that's the centripetal force keeping the system there. Okay, so that's the first one. The second one, how has our understanding of planetary motion changed historically? So history, well, this is a fascinating story. And if you're interested in physics, the formation of Newton's laws and that stuff, it is tied into the astronomy. It's tied into observing the planets. And so what I will say is I've heard people come up with flat Earth theory. Flat Earth theory has no ability at all to predict basic astronomy. And so if anyone's into flat Earth theory, you can take a look. There is even the simplest thing you could see in regular astronomy, flat Earth theory just it's absolutely nothing it can say about it. So what do I mean by that? Well, let's just take a look at one of the most basic observations you can do, which is watching the night sky. So here's something flat Earth theory has no conception of it. The spherical Earth theory easily describes this phenomenon. And that's how you know a good theory. What's a good theory? A good theory can describe many phenomena with only a few rules. You want minimum rules and maximum descriptive power. And so what we're looking at here is one night. One night. If you go out, and actually, this is actually near the equator. And I know it's near the equator because the point the stars are circling around is on the horizon. And so the round Earth theory says this. Say, here's the Earth. Here's the Earth. And it has an axis of rotation. It's rotating. And that's what causes the day, 24 hours of the day, this Earth is rotating. If I'm on the equator, I look to my horizon. There's the horizon. If I look to my horizon, what do I see? The axis of rotation. You got to, maybe I should draw this a little better. It's like you're looking far away. So it's like your horizon's going up like that. The axis of rotation is going up like that. What is the axis of rotation? That's the fixed point in the sky. For us, we call it the North Star, but it's not really a star. It's like a place in the sky. That's the axis of rotation. And so I know this picture was taken near the equator because this is near the horizon. You got the horizon is like right there. I mean, it's on a mountain, so maybe the horizon's up a little bit, but or maybe the fixed point is up a little bit. That's small, since that's a small distance, I'm saying this is on the equator. If this person was on the North Pole, the fixed point would be directly above. So if you're interested in this, search on the internet for, the stars rotating near the North Pole, then you got to look up to see that fixed point. But the idea is because the Earth is rotating, all the stars are moving together. So it was when they asked these questions about how has our understanding of planetary motion changed? Well, this sort of observation was telling us we live on a sphere. We live on a sphere because, well, the sphere model can describe if I go to one place, the fixed point is straight up. If I go to another place, actually, you're going to see two fixed points. If you're on the horizon, you'll see a fixed point when you look north. You'll also see a fixed point when you look south. And so these observations are all bared out. Like you can go anywhere on the Earth, and the height of the fixed point above the horizon, that's going to tell you where you are in your latitude and longitude. And I've seen people talk about flat Earth theory. I've read the stuff on the internet, and they have no conception of describing this. Some people mentioned it slightly, but they never. It's really hard to describe it. You can describe any location you're at, where is the fixed point by this simple model. That's what gives it some power. It can predict things. But there's sort of the fixed stars. And so you call these stars, like the celestial sphere. At the time, they thought the sphere was like an actual sphere, and we were like inside the sphere, and the sphere was moving together. These are all fixed stars with fixed locations. So like, you see the Big Dipper or you see other constellations, they're always the same distance apart, and they rotate together. And then there was these other weird ones, the planets. And planet, I believe, is in some sort of Greek is related to the word wanderer, because the planets, they move with respect to the other stars from night to night. And so this was the first thing about, it's a big deal. There's these other stars, these like really bright stars that they weren't part of this fixed thing. I mean, in one night, it would circle around just like the other stars, but from night to night, they were in different locations. And we start to see some different kinds of motion of those planets, or apparent motion. And so you get stuff like this, where this is Mars, and these are different nights. So it's like, you have like night 1, and then night 2, and then night 3. If you're watching Mars from night to night, this would be Mars. If you're watching it from night to night, it's at different places. Sometimes it does this, actually, it might not be night. It might be like week 1, week 2, more like that. But like over the course of weeks, it goes one way, and then it turns around, and then it turns around again. And so this is some weird motion. What do they call that? This weird name for it, like backwards motion or something like that. It's called the retrograde motion. And so you got to explain this. That's the idea about science, is why? Why is this retrograde motion happening? And so you have this two models. You have the Ptolemy model. And what is that? That's the Earth is at the center, and the planets orbit the Earth. This was the church model. This is what the Catholic Church was way into. Planets orbit the Earth. and the celestial sphere also orbits Earth. And so what they thought about it was, let's take a look at image. Right. And so here was the Ptolemy model. You got these epicycles. So the idea is epicycles explain the retrograde motion. And so what was the epicycle? It was like, well, they imagined the planet was going around the Earth, kind of going around the Earth. And then it was like doing these little cycles as it went around. And so it'd be like zoop, zoop. And that was producing the retrograde motion. Oh, that's possible. That was the Earth-centered model. But then there was a new model that came up. Let's take a look at the new model, was the Copernican model. Copernicus made a model. It's a different person. Call it the Copernican model. And what is that? That's sun-centered. That said that the sun was at the center. And this actually allows us to get rid of these epicycles. This was like a little addition that they had to make. And I'm going to come back to my idea here. I was trying to say earlier, a good theory describes many phenomena with only a few rules. That's what you want. You don't want to have 1,000 different rules. You just want a few. Just a few rules, a minimum number of rules. And so here's something. You got this retrograde motion. We're watching Mars. It's doing this weird circle. It's like, why does it do that? Maybe as it's orbiting the Earth, it has this little epicycle. It's like zooming around in some other like circle within a circle. That's okay. That's one possible way. The other possible way is sun-centered, or this is another suggestion. And sun-centered answers that question without the I'm sorry, where's my image? And so here is an explanation of retrograde motion with a Copernican model. You got the sun at the center, you got the Earth zooming around like this, and you got Mars zooming around like this. And the thing is, the idea about the Copernican model is that Earth orbits faster than Mars. And so Earth passes Mars in the orbit. And this also produced this retrograde motion. Basically, the Earth, let's say I'm looking up, I see the Mars over on my left side. Then a little bit later, at the same time of night, I see Mars is straight above me. And then a little bit later, I look up and Mars is over to my right. It moved from left to right. That's the retrograde motion. So it turned out this method also produced retrograde motion, but had no need for this other like little circle. You just have one circle instead of two circles. That's kind of an advantage. So the idea here, Copernicus model explained retrograde motion without epicycles. epicycles was like the little circle, and they thought maybe it's going in this little circle and that produces retrograde. But turns out if you do sun-centered, then you can get retrograde by this relative motion. But let's go through, your book does go through kind of a little historical sequence of the proving the Copernican model. So the idea about like this is modeling planetary motion. It took a long time to pull it together to Newton's laws, and it works like this. There's this guy, Tycho Brahe. He was the guy to take really good data on the locations of the planets. So he was a rich guy and he lived on like an island or something. And he took this beautiful data before telescopes, 1500s. This is pre-telescope. And your book has some beautiful artwork about him in his like device. But what did Tycho Brahe do? He took a very accurate data of planetary motion. Basically, he found out where the planets are and how, and where they go over time. So that was like the data guy. He took the data. And then you got Kepler. Kepler was Brahe's assistant. And so after Brahe died, Kepler analyzed the data. And so Kepler was living 1571 to 1630. And so he analyzed the data. And so he determined 3 rules. They're called Kepler's laws. And it works like this. 1, the planets travel in ellipses. That's the first one. We'll talk about what an ellipse is. It's like a circle. A circle is a type of ellipse. 2, equal areas in equal times. And I'll talk about that too. But the third one, there's a relationship between the semi-major axis and the period. And the third one is more mathematical. It works like this. The semi-major axis cubed is proportional to the period squared. So that's a mathematical one. But that's what Kepler did. He like analyzed Tycho Brahe's data. He found these laws. And then there's the third one, Newton. And this is what created modern physics, and that's the other thing. What I want to say about this is there's this idea about flat Earth and about how everything's made up and we don't know anything. But the history of physics, if you trust physics, you're going to have to get rid of flat Earth theory, because this is what proved Newton's laws in a way. Newton was able to rederive Kepler's laws using his physics, using his 3 laws. The second law, the third law, and the first law. So he uses 3 laws plus an idea about gravity he had the gravitational force law. So Newton came up with the gravitational force law. He then applied his 3 laws of motion, and he was able to rederive Kepler's laws. And that tells you a good theory. So you're able to he was able to use his mathematics to describe all of Tycho Brahe's data for a planetary motion, except for small things. But most of it was all taken care of. So that's the history they go through in the book. But let's do an example here. Oh, wait, first I need to go over these laws. So the planets travel in ellipses. What's an ellipse? So you might have played with ellipses in elementary school or something. If you have a fixed length of string and you tie it to 2 points and you trace, it'll trace out an ellipse. So it's it's a mathematical form where the sum of the distance from one focus to the other focus is constant. And so it traces out this thing. You've got these two foci, and the planets travel in ellipses. And the idea about that is that the sun is at one focus. So an ellipse has two foci, 1, 2, but it's kind of like the sun is at one of them. There's the sun. And then the planet, Earth or any other planet, is kind of following the path of the ellipse. So that's Kepler determined that from the data. The second one, equal areas and equal times. This one is related to angular momentum, but we're going to get to that in a later chapter. But what does it mean, equal areas and equal times? It means that, like, basically it moves slower when it's farther away from the sun. When it's way out here, it's moving super slow, 25 days, and it kind of spans this, it creates an area. So you've got this little area there. You call that area 1. And then you could do 25 days when it's nearby. It turns out it's going faster when it's nearby. So it comes zooming down in 25 days. And then you've got area 2. And the idea is those two areas are equal. Area 2 equals area 1. And this is true. You don't just have to do it for 25 days. Any amount of time you wait for, you're always going to cover the same amount of area. So this is Kepler 1, Kepler 2, and then Kepler 3 is this. There's no picture for Kepler 3. It basically says, as your semi-major, so what's the semi-major axis? You can see it here. It's like kind of you can think of the radius, the long radius. You can think of a ellipse as having two radii, one small or one big radius and the other small radius. I mean, they're not radii, but call it the semi-major and semi-minor axes. But basically this says that as the semi-major axis gets bigger, your period's going to get bigger. So if you're basically, the farther you are from the sun, the longer it takes for you to go around. And they got this relationship. Right, let's do a problem here. So they have us doing these different problems. Try this one here. So how long does it take Mars to complete one orbit around the sun? The distance of Mars from the sun is approximately 1.5 astronomical units. And they say here AU, astronomical units is AU, and AU is the average distance from the Earth to the sun. So an AU is like our radius, the Earth's radius. The radius of the Earth's orbit, our Earth, is 1 AU. And so they tell us our Earth 1 AU, our Mars 1.5 AU, and we have this beautiful formula that says basically A cubed divided by T squared. So you can write it different ways. I can say A cubed is proportional to T squared, or I can take the ratio, and that's going to be the same for all planets. So it doesn't matter. So, well, it doesn't matter if I'm considering Earth, Mars, or whatever. It's always basically the ratio of those two is the same. So think about it like this. A Mars cubed divided by T Mars squared, that's going to equal A Earth cubed divided by T Earth squared. And so what do we want here? We want to solve for T Mars. And so I see we want to get the thing we want to solve for by itself. There's T Mars. I want to get that by itself. So what can I do? Here's algebra. So what I'm going to do is I'm going to first multiply both sides by T Mars squared. And then two, what I'm going to do is multiply both sides by T Earth squared divided by A Earth cubed. So let's try the first one. The first one, I'm going to multiply. What do I have? I have this thing. There it is. So I'm going to multiply T Mars squared to both sides. And on the left side, it's going to cancel out. Canceling because it's on the top and the bottom. So it's going to cancel out. Then the next thing I'm going to do is multiply. So now I've got this. I've got A Mars cubed equals A Earth cubed divided by T Earth squared, and then multiplied by T Mars squared. I've got that, but I'm going to do the second thing, multiply both sides by that ratio. And so let's do that. So I've got T Earth squared divided by A Earth cubed. I'm going to do that on the other side. T Earth squared divided by A Earth cubed. And you can see what's going to happen. I'm going to cancel my A Earth. I'm going to cancel my T Earth. And I'm just left with T Mars squared. So I've isolated that. I wanted to solve for that, so I'm isolating that. And now I've just got this. T Mars squared equals T Earth squared. And then actually multiplied by the ratio of the semi-major axes. A Mars cubed, A Earth cubed. And that's actually the way to do it. Now I know all three of these things, or at least relatively. I know that the time the Earth, that's 1 year. We know that. That's the amount of time it takes to go around. The semi-major axis of Mars, 1.5 AU. Semi-major axis of Earth, 1 AU. So I'm going to put in those values. Well, first I'm going to take the square root. T Mars is going to equal the square root of T Mars squared. So I'm going to take the square root of T Earth squared and then A Mars cubed over A Earth cubed, like that. And then finally, we're going to get T Mars. Notice here I got the square root of something squared. And maybe I should go through it very slowly. So this could equal, well, it does equal T Earth squared square root multiplied by A Mars cubed over A Earth cubed. And that first term is just T Earth, because the square root of the square is just the value itself. So you got the T Earth, and then times the square root of A Mars cubed over A Earth cubed. Okay, so now let's just plug everything in. I got 1 year for the Earth's period, the semi-major axis of Mars, 1.5 AU, and that's cubed, and then divide by 1 AU cubed. And notice what's going to happen. I got AU on the top and the bottom and cubed on both cases, so it's going to completely cancel out. No more AUs. So really, this is the simple answer we're getting. It's basically 1 year times the square root of 1.5 cubed divided by 1 cubed, but you really don't need to write that because 1 cubed is 1. So you're just doing the square root of 1.5 cubed. That's really the whole thing. And we get 1.8. Oops. Somehow I thought it was more than that. Let me see if I'm getting the right answer here. Oh, that's it. 1.8 Earth years. That's how long it takes Mars to go around. Not quite twice as long. All right. All right, the next section we're going to look at is Newton's law of gravitation. This basically says all masses attract each other and how is that attraction actualized? By a force. And the force between two masses is going to equal a constant, which we'll call G, the products of the masses, M1 times M2, and then divide by the square of the distance. Actually, there's an image I think your book has here. It's gone. There it is. So it's like this. Gravitational force between two objects is proportional to the mass of each object and inversely proportional to the square of the distance between the centers of the masses. G times M1 times M2 over R squared, where G is a constant. The direction of the force is attractive and lies along the line joining the centers of the two masses. So the force, there's your line of force, there's your distance R, and there it's attractive. That's the general idea. And so how does this, relating this to planets is very cool. And so there's a drawing in one of Newton's books. It's like very similar to this drawing they have in our book. Actually, they recreated his drawing. Here it is. This is the idea. If I'm going to launch a projectile, you go up high, you launch it, it's going to come down. But the Earth is curved. So if I launch it fast enough, it kind of goes around the curve. If you launch it fast enough, it goes in a circle. And basically it falls, but it's constantly falling, but it never hits the ground. That's basically an orbit. An orbit is something that's constantly falling, but never hits the ground. All right. And so this is what satellites are doing. This is what the International Space Station is doing. So when they say 0 G, you see everybody floating around in the International Space Station. 0 G does not mean zero gravity, even though they're floating around and it looks like, oh, there's no gravity. Actually, if you are in the International Space Station, you're going in a circle. What does that mean? Let's say here's the International Space Station, the ISS. The gravity is there. If there was no gravity, the International Space Station would not stay near Earth. If there was no gravity, if we're really talking about zero gravity, like 0 G, zero gravity, then the International Space Station would go in a straight line at a constant speed and it would leave Earth and it would never come back. So the mere fact this space station stays near Earth means that there is gravity. Actually, the gravity at the location of the International Space Station is about 90% of gravity on the surface. So remember that. Just because they're floating around doesn't mean there's zero gravity. Why are they floating? Why are the astronauts, and I'm assuming you guys have seen images of the astronauts in the International Space Station. Why are they floating? Because they're in free fall. It's like a skydiver. They're basically skydiving up there, except there's no air. They're out so far that there's no air, but they're basically in free fall. Gravity's pulling down on them, but they're moving so fast that they don't hit the ground. So this little rule is actually able to drive orbits. And so Newton was able to use this rule to then describe the motion of all the planets. And this G thing, G is a number 6.67 times 10 to the minus 7 Newton meters squared over kilograms squared. That's a constant. We're not going to use that too much, but well, this book is actually, and I got the power of 10 wrong. We'll see. This book does like to do math a lot more than the other book I was using for this class. And I mean, this class officially has no math prerequisite, but this book is really asking you guys to do some harder stuff here. Yeah, they're asking you to actually calculate this stuff. Let's take a look here. Sample box 4, or example box 4. I thought it was 4, but it's only 3. All right, let's take a look here. Sample exercise, gravity, your weight, and the weight of the Earth. The mass of the Earth is 5.99 times 10 to the 24 kilograms. Its average radius, 6,370 kilometers. Find the gravitational force, the weight of a 50-kilogram person standing on Earth's surface. So we're going to use that formula. Let's see here. A, by using the gravitational acceleration. This one's easy. We already did that one. That's Fg equals the mass times G. So your mass, 50-kilogram person. This person weighs around 110 pounds. Got that times G, 9.8 meters per second squared. Let's see here, 450 plus trying to do it in my head. I'm gonna have to use a calculator here. 50 times 9.8. 490. So that's one way to do it. Let's use Newton's law of gravitation. So that's going to say the force of the sun. Oh, I'm sorry, we're doing the Earth here. So Earth on a 50-kilogram person, G times M1 times M2 over the radius squared. What we're doing something here that's kind of weird. We're approximating all the mass of the Earth as being at the center. Basically, all the mass we're assuming is at the center point, which is a little weird, but it turns out to be correct for a sphere. Basically, the sphere has mass everywhere. So in principle, you've got mass pulling you in all directions. I've got some mass pulling me one way, some mass pulling me another way. The gravitational law is saying all these little bits of mass are all pulling on you. And so the question is, what's the effect? And the answer is all the mass contained at the center. So it's nice and simple. And we're just going to plug in the numbers. So 6.67 times 10 to the minus 11 Newton meter squared over kilogram squared. We got that constant. That's like a conversion constant. Then just all the other stuff. You got the mass of the Earth, 5.98 times 10 to the 24 kilograms. You've got the mass of the person, 50 kilograms. And you're dividing that by the radius squared. So the radius, 6,370 kilometers. I'm going to write that 6,370 times 10 to the 3 meters. Get right like that. Or we could even simplify it a little bit more, which would be 6.37 and move decimal place over 3 spots, 1, 2, 3, times 10 to the 6 meters. And so I'm going to do that here. 6.37 times 10 to the 6 meters. And I have to square that. All right, so let's analyze the units here first. First, I got kilograms squared in the bottom. That's going to cancel my 2 kilograms in the top. And I remember that square and the radius, that has to square every single thing in the parenthesis that's multiplied together. And so you're going to square the meters, and those square meters are going to cancel with the square meters in the G constant. So what am I left with? I'm left with newtons. That's the only thing left. So now it's just calculator work. You've got 6.67 times 10 to the minus 11. You've got 5.98 times 10 to the 24. And then divide by 6.37 times 10 to the 6 squared, and that's all going to be in newtons. So plug that into your calculator. See what I get here. Probably should show you my split screen so you can see me how I'm doing the calculations. All right, here. And then we multiply by, and when I do all that, I get 491.49 newtons. These numbers, well, some of them was given to me in 3 significant figures, but another one only has 2. But this one has 3. Oops. 1, 2, 3. So I'm going to assume 3 significant figures. So that's going to round to 491 newtons. They're getting 490, but it's off by 1 newton. But that's the general idea. Actually, here 9.8 is only 2 significant figures. It actually should be 9.81. That might change it slightly. But they're almost the same. To 2 significant figures, they're the same. So that's the idea. That's a simple thing, you know. The same thing that gives us our weight is the thing that makes the planets go around, or at least keeps the planets going in orbits. Without gravity, the planets would move in a constant speed in a straight line. All right, this lecture has gone on for too long. We're at the very end here, 5.5, which is the moon and other satellites. And I'm not sure this is the most important section. It's not an astronomy class, but it is. There's a wealth of sort of examples here. Physics is tied into astronomy so closely. Like I said, Newton's laws were verified with observations of the planets. So if someone's going to claim flat Earth, they're also going to have to disavow the laws of motion that we use to make all of our cars and our airplanes and everything. The moon and other satellites. So the moon's going around us, and the sun is always lighting up half the moon at every single moment, except for when there's a lunar eclipse. Except for that moment, the sun lights up half the moon. But from our perspective on the Earth, we don't always see the lit up side. The new moon is when the lit up side is the opposite side. We can only see the dark side. And so this happens once a month, the new moon. And so you've got this dark moon. It usually appears right next to the sun. So you'll see it. Look at that crescent there. You see a little crescent. You're going to see a real narrow crescent like that. It's going to be, right near the sun. So it'll be right before sundown or right after sun, or right before sunrise or right after sundown. You'll see it. But then as it progresses in its little thing, eventually we can see half of it. So this would be like they call first quarter moon. You got the half moon. That could be like the first quarter. You got the new moon, and then you got the first quarter. That's like here. That's your first quarter. And then it keeps going around. It gets halfway around. Then we see the bright side. We call that the full moon. So that's like the second quarter. And then you got the third quarter. When it's almost done, you get another half moon, but it'd be like the other way. And that's the third quarter. Quarter meaning a fourth here. And then you get the new moon again. So it just keeps doing that. I guess that's the point of this section. I might stop with that. They go on how the Kepler's third law works for. This is just like the Earth and planet system. The moon's orbit is going to relate to its semi-major axis. It's going in an ellipse just like the planets are going in an ellipses around the sun, although it's going to be messed up by the sun there. The sun's going to pull on the Earth from the moon too, so that's going to affect it. But that's essentially the main points of this, so I'll stop there. All right, and so that's the lecture part of this.